had that as our integral one day, and it's like, there's nothing good that can come out of this. It's easy.
All right. Oh, yeah, we need this on.
Yeah, that's how that works. Yeah, it is. 25%. The law of large numbers. The law of medium numbers counteracts.
I never killed. I never killed.
Choices times choices times choices.
You don't kill kittens? No.
All right. So, in the last couple of sections, we have talked about we defined a derivative, and we saw that for r of t, r prime of t is tangent to r of t at t, and points in the direction of increasing parameter. If we interpret r of t as a position function, we can do that. We do not have to. It's not always, r of t does not necessarily always represent position. Then r prime is the velocity vector. It's often useful to think about r of t and r prime of t that way, just to help us interpret what we're doing. But r of t and r prime of t do not always have to represent a position and a velocity. So given that, what we're interested in today is to define specific unit tangent vectors and unit normal vectors. And we're going to use those to help us with our analysis of curves in terms of talking about curvature. So we're going to define the unit tangent vector. And we use capital T. Generally, t of t. And all we're going to do to define our unit tangent vector is normalize r prime. And this is, we're going to say where r prime is not 0. And that's what, another way of saying this is we're on a smooth curve. R of t represents a smooth curve. So this unit tangent vector is going to be useful to represent other properties of various curves. And we're going to use the unit tangent vector to get to our unit normal vector. But I want to do one example with the unit tangent vector that relates back to one of the problems that was on the board yesterday. All right, so we're going to say that r of t is the vector either minus t to cosine t to sine t. We want to find our unit tangent vector. find t, and then find a set of parametric equations for the tangent line at t0 equals 0, and then approximate r of 0.1. All right, before we find our unit tangent vector, what kind of curve is this?
A helix.
It's going to be a helix. So we get the circular motion, the circular motion in the y and z component. The e to the minus t is going to describe how the particle whatever moves along the helix. So it's a decreasing exponential function. So it's going to be, as we go along the curve, it's going to move less and less, right? Near the origin, it's going to be more stretched out, and then. All right, so let's do this problem. R prime. We need R prime, and we need the magnitude of R prime. R prime of t is negative e to the minus t minus 2 sine t and 2 cosine t. The magnitude of R prime. We need to normalize this for our unit tangent vector. Is going to be the square root of minus e to the minus t squared plus minus 2 sine t squared plus 2 cosine t squared. And what does this simplify to? E to the minus 2t plus 4, and we're taking the square root of that. Now, one thing I want to point out, so as a function of time, our unit tangent vector, because that changes in time, our unit tangent vector t would be 1 over the square root of e to the minus 2t plus 4 times this vector minus e to the minus t minus 2 sine t 2 cosine t. So the reason we're looking at for this at a particular time, but because we have this magnitude of r prime, the unit tangent vector, the expression for the unit tangent vector, we have this thing in the denominator. It's a little bit, it can get kind of messy. So keep that in mind as we move forward. All right. So r prime, so t at our unit tangent vector at time 0 is going to be this at t equals 0 becomes 1 over square root of 5. And this becomes negative 1, 0, 2. That would be our unit tangent vector at t0. Now, for the parametric equations of the tangent line, this tangent vector gives us our direction vector for our parametric equations for our tangent line. So I'm going to say t at 0 is in the direction of the tangent line. So our direction numbers I don't need to worry about this 1 over square root of 5. I can just use the negative 1, 0, 2. Our direction numbers are A equals negative 1, B equals 0, and C equals 2 for our tangent line. And we need a point on the tangent line to write our parametric equations. Well, a point on the tangent line is going to come from R at t0. So R of 0 is a point on the line. So R of 0, we plug 0 into our position. If we think of this as a position vector, if we plug 0 in there, our R of 0 is 1, 2, 0. So that's a point on that tangent line. So our equations for our line are x equals 1 minus t, y equals 2, and z equals 2t. Now, a more compact way of expressing that tangent line is that we could write, I'm going to write the tangent line, the vector equation of the tangent line at t0 as a function of t is r of t0 plus t times t at t0. So this would be the vector equation for the tangent line at t0. Yes?
Is that figure an L or a right angle?
This is an L for the line. So a compact way of notating the tangent line at a particular point. And then R to approximate, R at 0.1. So we're going to use the tangent line to approximate that. We're plugging in 0.1 into our equation for our tangent line because R at the particular point is the point that's on the line. So we get 1 minus 0.1, so we get 0.9, 2 because y is constant, and 0.2. So that would be the tangent line approximation for that value. All right, we good there? So now we have a method for finding a unit tangent vector. We want to find a specific vector orthogonal to t. Because if t is a tangent vector, a vector that's orthogonal to t would be a normal vector. And I'm going to say recall that if r dot r, this was one of our properties of a vector valued function, r dot r equals a constant, then r dot r prime equals 0. And I said we see this by finding the derivative with respect to t of the expression or the equation r dot r equals a constant. The derivative of a constant 0, derivative of r dot r is r dot r prime plus r prime dot r. So you get 2 of those equals 0. So r dot r prime is 0. We defined the way we define t, the way because we normalized it by normalizing, where we found it by normalizing the derivative vector r prime. T is a unit vector. So t dot t, if we dot t with itself, it's 1. Vector dotted with itself is its magnitude squared. T dot t is 1. And t dot t prime equals 0. So t prime is orthogonal to t. It would be normal to the curve. It would be normal to the curve, but it's orthogonal to t. So what we're going to do is normalize t prime, because t prime is not necessarily a unit vector. T is a unit vector, t prime is not necessarily a unit vector. Normalize t prime to define our unit normal vector. And we call it the principal unit normal vector. So the principal unit normal vector, n, is t prime of t over the magnitude of t prime of t. And we're saying where t prime of t is not 0. And r of t is smooth. So we need to be able to find a unit tangent vector, and we need t prime not to be 0. And the reason we call it, and I'll write the functional dependence here, n of t, because it varies in time. The reason we call it the principal unit normal vector is by defining it this way, n of t points to the concave side of the curve. Or we can think of it as pointing in the direction that if we're thinking of the object moving on this curve, it points in the direction that the object is turning. So our principal unit normal vector, we're going to use that when we talk about acceleration and our normal component of acceleration. Because the normal component of acceleration we expect has something to do with an object turning somehow. Now, when we found a unit tangent vector, when we found t, I pointed out that unit tangent vector, that because we had to normalize it, it has that radical quantity in the denominator. Well, now we have to find t prime and the magnitude of t prime. So finding the principal unit normal vector can be algebraically intense. I'll put it that way. Intense, yes. So you can, like I said, you can do it while camping. Intense. So keep that in mind when you're calculating your unit normal vector. Yes, it does get messy. And when we start talking about velocity and acceleration, when we want to talk about our tangential and normal components of acceleration, we're going to want to do that in a way where we don't actually have to calculate our principal unit normal vector explicitly. All right, so let's go through an example of finding a principal unit normal vector, and then we'll talk about a shortcut that we can use if our vector valued function is just defined in the plane. Not always going to happen. A three-dimensional vector valued function, finding the principal unit normal vector is messy. No matter what you do.
There's no way to avoid it being.
Right. So we want to find n of t, our principal unit normal vector, at t equals 2 for r of t. This is a simple function, t I hat plus 1/2 t squared j hat. What is this curve? Parabola. Y equals 1/2 x squared. So a simple curve, relatively simple, pretty simple functions. Well, let's take a look at finding our principal unit normal vector for this path. R prime is I hat plus tj hat. Magnitude of R prime is the square root of 1 plus t squared. So not bad functions here. Well, t as a function of time, our unit tangent vector, is just 1 over the square root of 1 plus t squared times I hat plus tj hat. Not a terrible function. Well, now we have to find t prime. And I'm going to use a product rule. This is a scalar multiple. So I'm going to use the scalar multiple product rule. So t prime is going to be the first, square root of 1 plus t squared, times the derivative of the second. So that's just I hat, no, just j hat. Oops, I don't need the brackets. I don't need the brackets. Those should just be parentheses. If I'm using I hat and j hat, I don't need the brackets. J hat, I was just excited about using vectors. It's kind of like the integral of the day. We have natural log squared. We have a vector. It's like, have you ever seen Airplane? Yeah. Yeah, doctor. Plus the second, so I'm going to do I hat plus j hat, tj hat. Times the derivative of this thing. minus 1/2 1 plus t squared to the negative 3/2 times 2t. So I get 1 over the square root of 1 plus t squared j hat. And then I'm going to, when I simplify this, I get a minus t over 1 plus t squared to the 3/2 I hat plus tj hat. Now I'm going to add those together. So minus t over 1 plus t squared to the 3/2 I hat plus minus t squared, that's this quantity, over 1 plus t squared to the 3/2 plus 1 over the square root of t squared j hat. Isn't that nice? And we can find a common denominator here in the j hat quantity because we're not in AP calculus anymore. This is minus t over 1 plus t squared to the 3/2 plus, find a common denominator here, and I get, this should be an I hat, plus 1 over 1 plus t squared to the 3/2 j hat. Because what I'm going to do to find my common denominator, I'm going to multiply this by 1 plus t squared over 1 plus t squared. And then the t squares cancel. And I have the t squared to the 3/2 in the denominator.
Wait, did we lose the negative that was?
No. So to find my common denominator here, I multiply this quantity by 1 plus t squared over 1 plus t squared. And so we have this numerator would be 1 plus t squared. So the negative t squared, they cancel. All right. So there's t prime. Now imagine if we wanted to find, we don't have to in this problem, but think about finding the principal unit normal vector as a function of time.
Please don't.
We have to normalize this.
How about we don't?
Now since this problem asks this, and that is going to make it even more messy. But we're looking for n at a particular point. So now we can substitute some values in. All right. So keep that in mind when you're calculating when you're finding principal unit normal vectors. Even it gets very messy. There's just no getting around it. T prime of 2. T prime of 2. I'm going to substitute a 2 in here. And I get a negative 2 over 5 to the 3/2 I hat plus 1 over 5 to the 3/2 j hat. And then we can find the magnitude of that. The magnitude of t prime at 2. So even calculating this at a point is not necessarily nice. Is the square root of minus 2 over 5 to the 3/2 squared plus 1 over 5 to the 3/2 squared. So we have this very lovely quantity. And luckily this simplifies pretty nicely. This is, we get a 5 in the numerator, and we get a 5 to the 3rd in the denominator. So this simplifies to 1/5. 2 squared plus 1 squared is 5 in the numerator. 5 to the 3 halves squared is 5 to the third, so you get 5 over 5 to the third.
So it's going to be 1 over 25.
1 over 25 and the square root of 1 over 25 is 1/5. All right, so finally, n, our principal unit normal vector, at 2 equals 5 times this thing. The other thing I want to point out here is this is a 2-dimensional vector. If you're doing this for a 3-dimensional vector, you're going to have another component here. It's even more. And I could simplify this. 5 over 5 to the 3 halves is square root of 5 over 5.
Simplification.
All right. Questions? So we can see that finding the principal unit normal vector can be algebraically difficult. In the plane, I want to show you a shortcut. In the plane, in the plane only, if t as a function of t is x of t I hat plus y of t j hat, we know that the way we've defined t is a magnitude of t is 1. So this tells us that the square root of x of t squared plus y of t squared equals 1. And we know that n and t are orthogonal. So in the plane, we can think of t as a line and our principal unit tangent vector is a line, and our principal unit normal vector is a line. How do we find a line that's orthogonal to another line, that's perpendicular to another line? Yeah, we can the slopes of perpendicular lines are negative reciprocals. So we can use the negative reciprocal of the slope, and I'm going to put slope in parentheses or in quotes. We can think of t as having a slope. Technically it does, but we usually don't talk about the slope of vectors. We can use the negative reciprocal of the slope of t to find n. So n is either, in this case, to have a negative reciprocal slope, n is either n equals y of t I hat minus x of t j hat, or minus y of t I hat plus x of t j hat. And since t is a unit vector, n is going to be a unit vector also. So we don't have to normalize it, because the square root of y of t squared plus x of t squared is 1.
Can you do this with
No.
Honestly.
How do we pick between these two, though?
Plug them in and test it. Thought the
Yes.
Well, we're guaranteed that either of these is going to
Oh,
be
you find the
orthogonal.
side.
We have to pick the one that points
Yeah.
to the concave side of the curve.
So yeah, you need to, can't look at the graph. with
You
the
have to
side.
be able to visualize the graph somehow and pick the one that points to the concave side of the curve.
Pick one that's good.
The other one's going to point the opposite direction.
And then there's no nice neat trick for three-dimensional. It's just
No.
a complete mess no matter how you visualize it.
Yes.
Good. Fantastic. That's going to be a great time.
So our from here on out, Calc, especially with the derivatives, when we're talking about derivatives, which with vector valued functions, we're talking about derivatives now. When you talk about derivatives, you end up doing a lot of algebra. There's no way around it. And because we're in 3 dimensions, you do more algebra than you do in 2 dimensions.
Why? Why would anybody think that we
No, I got it. It's all.
You have a curve like this. This part is no, it's not. That's that.
848.
It's always concerning to see homework this short.
I will guarantee you that some of these problems are not particularly fun.
But then why are we doing them? Math is supposed to be fun. So math
These